I am currently working as an assistant professor at the Department of Chemical Engineering at Caltech Dr. Raghunaran Dr. Sakutala Engineering College. Today I am here to give a small lecture on phase diagrams for binary solutions. Phase diagram for binary solutions.
Okay, now let's see what is meant by phase diagram and where we used it and how the phase diagrams are constructed. First, we need to know what is meant by phase diagram. Phase diagram is nothing but it is a graphical representations where there is a coexistence of two phases at a certain range of pressure for a given temperature. Then the phases are either liquid, vapor and solid. Then the second thing is we need to know where we use the phase diagrams. The phase diagram is a key tool to understand or to explore the phase equilibria, that is to visualize the changes happens in the system. Then what is meant by phase equilibria? It is a term used to describe or to study the relationship between the two or more phases which exist in the equilibrium state. This is known as phase equilibria. Then when the system is said to be equilibrium, when there is no changes is possible, then the system is said to be an equilibrium. Then the phase diagrams are represented by three types. That is PXY phase diagram, TXY phase diagram and XY phase diagram. Then what is meant by PXY, TXY and XY? PXY is nothing but the pressure composition phase diagram which represents the phase behavior of a system or a component at a constant temperature. Then TXY phase diagram, that is nothing but temperature composition phase diagram which represents the phase behavior of a system or a component by keeping the constant pressure. Then XY phase diagram, it is nothing but the equilibrium diagram or a distribution diagram. Here also we are going to keep the pressure as a constant one. Okay, now let's see the constructions of phase diagrams. Here, the first construction is TXY phase diagram, that is temperature composition phase diagrams. Here we are going to set the pressure as a constant one. First, we need to consider a binary system which is made up of two components, that is A and B. Here, assume A is more volatile than B. That is, volatile means the vapor pressure of A is greater than the vapor pressure of B at a given temperature. Then, according to the Gibbs phase rule, for a binary mixture, the number of degrees of freedom is always 2, which is calculated by using the formula F equal to C minus P plus 2. Here then the BLE data, that is vapor liquid equilibrium data, which is represented by the temperature composition diagram at a constant pressure. TXY diagram is also known as boiling point diagram, which is boiling point diagram or a distribution diagram, that is equilibrium diagram. As I said before, the boiling point diagram is also known as TXY diagram, that is temperature composition diagram. Here we are going to plot a graph between temperature and the composition of liquid and vapor, that is temperature versus XY curve. Here the temperature is placed in the y-axis and the composition is placed in the x-axis. From the graph we get two curves, that is upper curve dew point curve and lower curve bubble point curve. These points are clearly explained in the graph. And this is the graphical representation for the boiling point diagram. Here, as I said before, consider the two components A and B. From the graph, we get upper curve and the lower curve. The upper curve is known as T, Y curve, that is temperature vapor curve, and the lower curve is temperature liquid curve. The upper curve is also known as dew point curve and the lower curve is known as bubble point curve. And consider a mixture whose temperature and composition is represented by the point A. To be more clear, the point A which represents the liquid state, that is below the lower curve, the liquid is in a fully liquid state, that is super cool liquid. And then point B represents the bubble point and the point H represents the dew point and the point J represents the vapor state, that is where the vapor is superheated vapor. and the point B2H represents the equilibrium state where it contains both liquid and vapor and it is going to attain the equilibrium state. And these are the points which is general in the graph. And now, for example, we are going to heat up water at a constant pressure. We are going to keep the pressure as a constant one. And initial stage, the water in the liquid state, that is point A, once it reaches the maximum temperature, the boiling point of the liquid, it attains the boiling point of the liquid and starts to get a first bubble, that is B, point B, which means bubble point temperature. What is mean by bubble point temperature? It is the first bubble of water, the point where we get the first bubble of the water, which is known as bubble point or the bubble point temperature. Then it reaches from the temperature T2 to T1 and now the liquid starts to boil. We get some vapor which is represented by the point C and now connect the line B to C by a dotted line which represents a tie line, which means the tie line consists of both liquid and vapor. And why? Because it is known as tie line, mean because the point B and C has the same temperature as T1 and it also having the both liquid and vapor phase. On the further heating, the system will result in the vaporization of more liquid and rises from the temperature T2 to T1, means T1 to T2. And the system consists a saturated liquid state, which is represented by point T, and the saturated vapor, which is represented by the point E. And the D and E is also connected by a tie line because this is the point where the liquid and vapor going to get the equilibrium state. Since the vapor phase is not fully removed from the system, the original mixture composition of original mixture is equal to the composition of combined mixture because we didn't remove any vapor from the system till now. That's why here the composition is not changed, but the relative amount of the liquid and vapor is changed because we kept the pressure as a constant and not the temperature one. So the relative amount which is depend on the temperature only. If the temperature increases, the relative amount change. If the change according to based on the increased or decreased, which is the relative amount. What is meant by relative amount? The relative amount is nothing but the ratio between the liquid, the composition of liquid to the composition of vapor. That is EF to the DF, which means relative amount, which is equal to amount of liquid EF divided by DF, that is amount of liquid by amount of vapor, which is known as relative amount and which is noted as a point F. Then the heat, while the heating is given continuously, the temperature rises from T2 to T3 and the point G represents the last drop of the water. Liquid gets vaporized and then the H point represents the composition of the combined mixture and the original mixture. This is the point where the last drop of vapor we get, that is the liquid is fully vaporized from initial stage to final stage, and the point H2J which represents the vertical line which represents the cooling state. We are going to cool down the vapor. So by this we get the dew point, which is the first drop of condensate where we get, that is known, that's why this H is known as dew point curve. Here the first drop of condensate is formed and here the last drop of condensate is formed. Now, at a given pressure, the temperature during the vaporization of solution varies from boiling point to the dew point. And then the next diagram is equilibrium diagram, which is known as XY diagram. That is, we are going to plot the graph between X versus Y, X in the Y axis and Y in Y axis. Here we are going to draw the diagonal line, which is Y X equal to Y, that is Y equal to X. The both composition are same, which is explained clearly in this graphical representation. This is graphical representation for the equilibrium diagram. As I said, y, we place the y in the y-axis and x in the x-axis. This is a diagonal line where y equal to x, that is the composition, where the center part of the curve, that is we didn't remove the any mixture or any vapor from the system. So that's why the diagonal line, which is y equal to x, and this upper curve which represents the more volatile curve, that is the ty curve. That's why it lies above the diagonal line, and the point P represents the boiling point. That means the point where the liquid or vapor going to get the equilibrium state, and which is noted from the diagram, that is point B and C, where the point B and C gives rise to the point P, which represents the equilibrium state. This is the graphical representation for the equilibrium diagram. And here, if the Txy curve is very close to the diagonal, which is this curve, which is very close to the diagonal, means the composition of vapor is not much more than the composition of liquid when the system is in equilibrium. When the curve coincides with the diagonal, then the composition of liquid, which is equal to the composition of y. Till now, we see the boiling point diagram and equilibrium diagram, that is xy diagram. In that both we keep the pressure as a constant one. Consider if pressure is changed in the diagram, what happens in the boiling point diagram, and then xy diagram, that is equilibrium diagram. We are going to see that the effect of pressure on the VLE, that is vapor liquid equilibrium phase diagram. What happens if the pressure changed while the water is boiling? In the both, we kept the pressure as a constant. Now, if consider if the pressure is changed. Generally, we know the boiling point of the pure substance is increases with the pressure. That is, consequently, the boiling point diagram at high pressure will above the boiling point diagram at the low pressure. Generally, we know that the relative volatility, which is similar to the relative amount, the relative volatility is decreases with increases in the pressure. And then there is a formation of loop in the graph. This is a graphical representation for boiling point diagram and XY diagram. This represents the formation of loop curve, and this represents the formation of narrow slit. This is the formation of loop curve in the dew point and the formation of narrow slit in the bubble point. Why there is a formation of loop curve and narrow curve? The narrow curve is general, which shows the effects of pressure in the boiling point. This loop curve is formed because the P3 represents the critical pressure. Once the pressure reaches the critical pressure or cross the critical pressure, the curves became shorter. That is, the effect of the relative amount is decreased based on the pressure. That's why we get the looped curve. The looped curve is formed on the dew point, and the P5, P4 represents the curve became shorter, that is relative amount which is decreases while increasing the pressure, that is when reaches the critical pressure, the relative amount and the relative volatility gets decreased. And this is the representation of effect of pressure on the BLE, that is phase diagram, both liquid and vapor, XY and boiling point diagram. And now we are going to construct the last diagram, that is PXY phase diagram, that is pressure, composition, phase diagram, that is constant temperature equilibrium. We are going to keep the temperature as a constant one. And here also we are going to consider two components, which is A and B. Here assume A is more volatile than B, that is liquid is more volatile than the vapor. In that boiling point diagram we see vapor is more volatile than B, and in this we see A, that is liquid is more volatile than B. So we get the tilted curve in the graph, that is similar, same similar curve, but the curve is tilted, that's opposite to the boiling point diagram, which is why we already know that the vapor pressure of A is greater than the B here. So A is greater than B, and PB represent the vapor pressure of B, PA represent the vapor pressure of A. And now we are going to see the graphical representation for the PXY diagram. Here we are going to plot the graph between pressure and XY, that is mole fraction, composition of the liquid and the vapor. We get we consider a point A and B, that component, and we get the curve, upper curve and the lower curve. The upper curve which represents the Px curve, that is boiling point curve, and the lower curve which represents the Py curve, that is vapor curve, which represents the dew point curve. And then here also some general points, that is C, D, A, B, E, F. C which represents the liquid state, and D represents the boiling point, bubble point state, and E represents the dew point, and F represents the vapor, and AB represents the tie line. Yeah, the procedure is same as the boiling point diagram, but the notations are different here. As I said before, C, consider C is the liquid. We are going to consider a mixture whose temperature and composition is represented by point C. The above the upper curve, the position means the liquid is fully liquid, which is super cool liquid, and below the lower curve the vapor is superheated vapor. And then we are going to increase the pressure, that is C to D. The point moves from C to D. Here the first bubble of the water we get, and then while further increasing with the D to E, which represents the equilibrium state, and A to B, which represents the tie line. That is, we are going we are having both the liquid and vapor phase at the same temperature, and E represents the last drop of the vapor, but liquid gets vapor, and F represents the first drop of condensate we get after the cooling. The one only one thing here different is we are going to keep the temperature as a constant one. We are going to increase the pressure, and this diagram represents the effect of temperature. As we see before, the effect of pressure on the both diagrams. Here we are going to see the effect of temperature on the PXY diagram. Here also same, if the temperature, that is here the temperature which crosses the critical envelope, that is critical temperature. Here also we form the looped curve in the dew point, and the narrow slit in the narrow curve in the bubble point. This is also same as the effect of pressure on the BLE. And then our next topic is VLE for non-ideal solution, that is vapor liquid equilibria phase diagrams for non-ideal solution. We already know that what is meant by non-ideal solution. Non-ideal solution is nothing but the solution which does not obey the Raoult's law, which is known as non-ideal solution. Mostly some solution extended the little bit deviation from the ideal behavior, and the deviation of ideal solution is classified into two types, that is positive or negative deviation. And the deviation means the classification of deviation is based on the pressure which is present in the solution and to the pressure which is calculated by the Raoult's law. The deviations which is classified based on the pressure which is exerted in the solution is greater than or less than the predicted by the Raoult's law. Then here the non-ideal solution which is demonstrated using the graphical representation, which is Pxy diagram. Here we are going to keep the temperature as a constant one. When the total pressure of the system is less than the ideal value, then the system is deviate negatively. For this case, the activity coefficient for both A and B is equal to 1, and the P versus X curve is located below the straight line. This is a straight line which is located below the straight line, which represents the deviation as negative, and the total pressure is greater than the ideality deviation, then the deviation is positive, and the activity coefficients for both the liquid and the vapor is greater than 1, and which is the P versus X curve, which is located above to the straight line, which represents this graph represents the negative deviation, and this graph represents the positive deviation. That is, the pressure which is exacted from the graph which is greater than the predicted by the Raoult's law. So here the activity coefficient is greater than 1, and this is the pressure what we are extracted from the solution, which is less than the predicted pressure predicted by the Raoult's law. Here the activity coefficient for both the liquid and gas phases is less than 1. So the P versus X curve lies below the straight line. And here we are going to see the example for non-ideal solution, which is azeotrope. This is the best example for the non-ideal solution. And then what is meant by azeotrope? Azeotrope is a constant boiling mixture, which means there's a boiling of solution without changing in the composition, which is known as azeotrope. This is azeotrope is boiled, which results in the vapor will have same composition as liquid from which it produced. As I said before, there is a boiling in the liquid without changing in the composition. This is known as azeotropes. And then azeotropes are formed by two types, which is large positive deviation and negative deviation from the ideality behavior. This is non-ideal solution. If the deviation is positive, will leads to the maximum in the vapor pressure curve, and the deviation is negative will leads to the minimum in the vapor pressure curve. As I said before, the azeotrope is characterized based on the deviation, which is minimum boiling azeotrope and the maximum boiling azeotrope. These are the types of azeotropes. And then the first type is minimum boiling azeotrope. The minimum boiling azeotrope, the solution which shows the positive deviation from the ideality in certain cases may lead to the formation of azeotropes in the minimum boiling time, which is represented by the graph, that is pxy, dxy and xy curves. Here, this is a graphical representation for the minimum boiling azeotropes. This is graph representation for Pxy, which is constant temperature, and this is for Txy, where here we keep the pressure as a constant, and this is a equilibrium diagram. And this is the graph which represents the pressure composition diagram. The pressure is plotted in the y and the composition is plotted on the x. We keep the temperature as constant. The upper curve which represents pressure liquid curve and the lower curve represents the pressure vapor curve, and the point M which represents the formation of azeotrope, that is azeotropism. Here the point M is a tangent between the x and y curve, and here there is a little bit deviation which represents the formation of original mixture, that is combined mixture composition which is equal to the original mixture, and the point M represents the formation of azeotropism. Here there is a small deviation which leads to the tangent coincide of the curve. Here the composition is same as the original mixture, and then this represents the Txy diagram, that is temperature versus xy diagram. Here we are going to set the pressure as a constant one. Here the vapor curve has more volatile, so it's is in the upper curve, and the Txy, that is a less volatile, so that's why it's in lower curve. Here the temperature is minimum. In the minimum temperature itself, the curve which coincides and form the tangent point, which is M. Here in this at this point here the azeotropism is formed while the P and Q is boiled, and similar to the same, these both diagrams are same, but here the volatility of A and B is different from this curve, and this is equilibrium diagram, as we said before in the boiling point diagram, where the point the equilibrium starts, which is denoted as a, there we denoted as a P point, here we denoted as a M point. At the point of M we are going to get the equilibrium state of the liquid. This is the graphical representation for the minimum boiling azeotrope. As similar, we are going to see the maximum boiling azeotrope, which means the solution showing the negative deviation from the ideality, which forms the maximum boiling azeotrope. This is also explained with the example. In this graph, we are going to see the representation. We are going to see the representation of pressure XY diagram and temperature XY diagram and the equilibrium diagram. Here both Txy and Pxy we are going to keep the pressure as a constant, and Pxy we are going to keep the temperature as a constant. As usual, same as the minimum boiling azeotropism, but there is a difference between in these two graphs. In the minimum boiling azeotropism, we get the maximum of pressure in the maximum of temperature in the pxy diagram. It's maximum of the curve is tilted. Here we get at the low pressure itself we get the composition azeotropism is formed, and same as the txy diagram we get the critical at the critical temperature we get the azeotropism. As I said before, in the equilibrium diagram, we get a point as a P, which is represents the equilibrium state, which rises from the tie line. Here also, the rises of tie line P are to QS, the point is represented by M, where the liquid and vapor which gets the equilibrium state and represents the deviations. And this is the difference between the minimum boiling point azeotropism and maximum boiling azeotropism. The only thing different is the vapor curve, means the volatility vapor curve, and the point deviations, less deviation and more deviation. The less deviation, which is negative deviation shows the maximum boiling azeotrope, and the positive deviation shows the minimum boiling azeotropes. In the next session, we see the VLE, that is vapor liquid equilibrium for the ideal solutions. I hope this session will help you to understand the phase diagrams for the binary solution. Thank you.